Good morning. Let's embark on a comprehensive exploration of battery energy storage systems, BESS, with a primary focus on thermal runaway protection mechanisms and UL standards. My name is Tony Rogers, and I have dedicated my career to pushing the boundaries of energy storage technology. Today, I am thrilled to take you on a journey through the intricate details of fire suppression systems, specifically UL 9540 and UL 9540A standards. Additionally, we will delve into the advanced design characteristics and functionality of UVR, under voltage release, and shunt trip mechanisms on breakers and coils, highlighting their critical role in controlling dampers, fans, louvers, and molded case circuit breakers, MCCBs. Furthermore, we will emphasize the paramount importance of temperature monitoring and control. To add another layer of technical depth, we will explore the significance of UL 1973, which specifically addresses batteries used in stationary applications. Lastly, we will unravel the advantages of active state of charge, SOC, cell rebalancing on lithium iron phosphate, LFP cells. Prepare to immerse yourselves in a realm of technical expertise within the battery energy storage systems domain. Ensuring the safety and reliability of battery energy storage systems necessitates the implementation of robust fire suppression systems. These meticulously designed systems are not only capable of detecting fires, but also suppressing them, effectively impeding their spread and minimizing potential damage. In the context of BESS, these systems play an indispensable role in mitigating the risks associated with thermal runaway events, which have the potential for catastrophic consequences. To uphold the highest safety standards in BESS installations, the Underwriters Laboratories, UL, has developed two pivotal standards, UL 9540 and UL 9540A. UL 9540 sets forth comprehensive requirements for energy storage systems, encompassing batteries, power conversion equipment, and associated components. This standard provides essential guidelines for manufacturers, system integrators, and regulatory bodies, ensuring that BESS installations adhere to rigorous safety criteria. In addition, UL 9540A specifically focuses on evaluating the fire performance of energy storage systems. It scrutinizes various aspects, including fire propagation, thermal runaway characteristics, off-gas characterization, and system-level testing. Adherence to these UL standards is crucial to guarantee the highest level of safety in BESS installations and inspire confidence among stakeholders. Supplementing the UL standards, the National Fire Protection Association, NFPA, has also developed indispensable guidelines pertinent to BESS safety. NFPA 68 offers recommendations for venting deflagrations in enclosures. This standard delves into various considerations, such as deflagration characteristics, vent sizing, and proper design approaches to mitigate hazards associated with gas releases. Complementing NFPA 68, NFPA 69 focuses on the prevention and mitigation of deflagrations in vented enclosures. It encompasses critical aspects, including the determination of safe deflagration venting areas, explosion prevention strategies, and the application of suppression systems. Compliance with these NFPA guidelines ensures a holistic approach to BESS safety, encompassing both ventilation and explosion prevention measures. Another critical NFPA standard that demands our attention is NFPA 855, which specifically addresses the installation of stationary energy storage systems. NFPA 855 encompasses a comprehensive set of requirements that span multiple disciplines, including fire protection, ventilation, electrical equipment specifications, and emergency disconnecting means. This standard provides essential guidance on critical aspects, such as the selection and installation of fire suppression systems, ventilation design considerations, electrical equipment requirements to ensure safe operation, and the establishment of emergency disconnecting means for rapid shutdown in hazardous situations. Adherence to NFPA 855 is indispensable to ensure the utmost safety in BESS installations and mitigate potential hazards that may arise. Expanding our technical exploration, let's now delve into the significance of UL 1973 in the context of battery energy storage systems. UL 1973 specifically addresses batteries used in stationary applications, including those found in BESS installations. This standard outlines comprehensive requirements and test procedures to evaluate the safety and performance of these batteries. UL 1973 covers various aspects of battery design, construction, and performance. It includes criteria for thermal stability, electrical performance, mechanical integrity, and environmental compatibility. The standard ensures that batteries used in BESS installations undergo rigorous testing to assess their ability to withstand potential hazards, such as thermal runaway, overcharging, or short circuits. Compliance with UL 1973 provides assurance that the batteries employed in BESS installations meet the highest safety and performance standards, enhancing overall system reliability. Now let's shift our focus to the advanced design characteristics and functionality of UVR, under voltage release, and shunt trip mechanisms on breakers and coils, further emphasizing their crucial role in controlling various components within BESS installations. UVR mechanisms monitor the voltage levels in the system and release the hold on the breaker's operating mechanism when the voltage drops below a predetermined threshold. This enables the breaker to trip and disconnect the power supply to the affected circuit. By utilizing UVR mechanisms, it becomes possible to rapidly isolate faulty equipment and prevent further damage or hazards. Similarly, shunt trip mechanisms provide an additional layer of protection by introducing a controlled short circuit to the breaker's coil when a specific condition is met, causing the breaker to trip and interrupt the power supply. These mechanisms are typically employed in scenarios where immediate disconnection is necessary, such as during an emergency shutdown or when predetermined safety thresholds are exceeded. These design implementations of UVR and shunt trip mechanisms play a critical role in the control and operation of various components within BESS installations. For example, they can be utilized to control the position of dampers, fans, and louvers, ensuring proper ventilation and heat dissipation to prevent overheating. Additionally, they can be used to trip MCCBs, molded case circuit breakers, isolating sections of the system in the event of a fault or abnormal condition. Moving on to temperature monitoring and control, it is paramount in BESS installations to maintain safe and optimal operating conditions. Advanced temperature sensors are employed to continuously monitor the temperature of batteries and associated components. This real-time temperature data is crucial for identifying potential issues and triggering appropriate safety measures. Effective temperature control mechanisms, such as active cooling or thermal management systems, are utilized to regulate and maintain optimal temperature levels within the system. These systems employ various techniques, including air or liquid cooling, to dissipate excess heat and prevent thermal runaway events. By closely monitoring and controlling the temperature, the risk of cell degradation, thermal instability, and potential hazards is significantly mitigated. Lastly, let's explore the advantages of active state of charge, SOC, cell rebalancing, specifically on lithium iron phosphate, LFP cells. Active SOC cell rebalancing is a technique employed to maintain uniform cell voltage levels within a battery pack. It involves redistributing the charge among individual cells to ensure consistent performance and extend the overall lifespan of the battery. In the case of LFP cells, which inherently exhibit excellent thermal stability and resistance to thermal runaway, active SOC cell rebalancing further enhances the performance and safety of the battery. By equalizing the charge distribution among cells, it minimizes the likelihood of overcharging or undercharging individual cells, which can lead to imbalances and potential safety risks. This technique optimizes the overall performance, efficiency, and longevity of the battery pack, making it a valuable asset in BESS installations. In conclusion, we have delved into the intricate technical details of battery energy storage systems, BESS, exploring fire suppression systems, UL standards, including UL 1973, and the design characteristics of UVR and shunt trip mechanisms. We have also emphasized the importance of temperature monitoring and control, as well as the advantages of active SOC cell rebalancing on LFP cells. It is through adherence to these standards, the implementation of robust safety mechanisms, and the utilization of advanced monitoring and control systems that we can ensure the utmost safety, reliability, and performance of battery energy storage systems. By following the guidelines outlined in UL 9540, UL 9540A, NFPA 68, NFPA 69, NFPA 855, and UL 1973, we can establish a strong foundation for the safe deployment and operation of BESS installations. These standards provide a comprehensive framework that addresses various aspects of safety, fire protection, ventilation, electrical equipment requirements, and battery performance. Furthermore, the integration of UVR and shunt trip mechanisms on breakers and coils offers precise control and protection within BESS installations. These mechanisms enable quick response and isolation of faulty equipment, minimizing potential hazards and damage by actively monitoring voltage levels and introducing controlled short circuits when necessary. These mechanisms contribute to the overall safety and reliability of the system. Temperature monitoring and control are crucial for maintaining safe operating conditions in BESS installations. Advanced sensors and control systems continuously monitor the temperature of batteries and associated components, allowing for timely detection of abnormal temperature rises. This data is utilized to trigger appropriate safety measures, such as emergency shutdown or activation of fire suppression systems, ensuring the prevention of thermal runaway events and associated risks. Lastly, active SOC cell rebalancing provides an effective method for maintaining uniform charge distribution within LFP cells. By equalizing the charge among individual cells, active rebalancing minimizes the potential for overcharging or undercharging, which can lead to imbalances and compromise battery performance and safety. This technique enhances the overall efficiency, longevity, and reliability of the battery pack, making it a valuable feature in BESS installations. Thank you for tuning in today. I wholeheartedly appreciate it.